So this is what we call squeezing theorem. Let's see some examples. Uh, Calculate the limits of the sequences. A is 2n squared minus n minus 1, 5n squared plus n minus 3. B is cosine n divided by n, and C is square root of n squared plus 2n minus n. Alright, solution. Let's look at the first one. What we will do, you may either use the definition of epsilon delta epsilon definition of limit, or use the rules we have seen so far, or the things we have proved so far. Using the epsilon definition for these limits is not practical, but we can make use of the following, facts. Let's consider the first one. I can make use of all the facts I have stated so far. Here I stated several, rules. I didn't prove any of them. Actually, they can be proved using the definition, but it is not the content of this course. Therefore, we just take them as granted. Okay, they are kind of obvious facts, but actually they can be proved rigorously. This is what we do in math courses. Here we can do the following. You see, I can divide both numerator and denominator by n square, and I get this. And you see here, I can delete n squares, and we get this. Limit as n goes to infinity, 2 minus 1 over n minus 1 over n squared, 5 plus 1 over n minus 3 over n. Now, what do we know about this? Uh, the So this is the ratio of two terms, right? This term divided by this term. If both uh, terms have limit, and if the limit of the denominator is not 0, then I can write the limit as the ratio of the limits. So I can look at both numerator and denominator separately. The denominator, numerator is this. So it's a sum of three sequences. This sequence, and then this one and this one. Sum or difference. Well, this sequence is the constant sequence, right? 2, 2, 2, 2. It's constant sequence. What is the limit? Limit is just, of course, 2, right? It's constant function 2. So the limit is 2. What about 1 over n? Well, we showed that this has limit 0. What about 1 over n squared? Well, 1 over n squared is just 1 over n times 1 over n. And each one goes to 0. Therefore, the product is going to 0. Okay? So this will go to what? This will go to 2 minus 0 minus 0, which is 2. So this will be limit of this, which is just 2, divided by, what about this one? This will go to 0. This will go to 0. this should be n squared, right? In a similar fashion. So this will go to 5. So the result will be 2 over 5. Here, if you want to write this, in more detail, we can do the following. Right? So this goes to 0. This goes to 0. Sorry. Uh, so uh, limit of 1 over n is 0 is known. 1 over n squared is just 1 over n times 1 over n, and thus limit of 1 over n squared. Since both of them has limits, this can be written as like limit of 1 over n times limit of 1 over n, which is just 0 times 0, which is 0, right? And 2 over n is just 2 times 1 over n, right? And thus uh, limit of 2 over n is just 2 times limit of 1 over n. So this is just 2 times 0, which is 0. Hence, limit of 2 minus 1 over n minus 1 over n squared is just 2 minus 0 minus 0, which is 2. Similarly, limit of 5 plus 1 over n minus 3 over n squared. What is this? It is the denominator term here. 5 plus 1 over n minus 3 over n squared. What is this limit? Limit of 5, which is 5, plus limit of 1 over n, which is 0, minus 3 times 1 over n squared. 1 over n squared has already limit 0. So 3 times that will have 3 times 0, which is just 0. So this limit is 5. Hence, hence limit of 2n squared minus n minus 1 divided by 5n squared plus n minus 3 is just 2 over 5. Okay? All right. Evet. Yeah. You should, I am sure that whenever you see this, you can just write down this, right? 2 over 5. But we want, the details. How you arrive at this, result. Knowing the answer is not doesn't mean much. Okay, you have to explain why that's the correct answer. Okay, uh, I have this cosine n divided by n. What about this one? Well, here we use squeezing theorem. Uh, note that cosine n is always between 1 and minus 1 because cosine function always takes values between 1 and minus 1, whatever you put inside. And thus we have this 1 over n, cosine n over n, and 1 over n. Also, limit of 1 over n and limit of minus 1 over n are both 0. And thus, by the squeezing theorem, this is convergent. Cosine n over n, this limit exists and equals 0, right? If both of them goes to 0, then the middle term should go to 0, right? That's the result. We usually write it this way. So 1 over n, 1 over n. This goes to 0. This goes to 0. Therefore, this goes to 0. Okay. And the last one, the limit n squared plus 2n minus n. This expression. Here, I cannot make use of the rules I have stated because n squared plus 2n goes to infinity. Its square root will go to infinity. This will go to also infinity. So both terms are going to infinity and you'll get the difference. You don't know what it is, right? However, there is this trick. You multiply both this expression and the denominator with the conjugate of this. What is the conjugate? Well, here it is. N squared plus 2n plus n. And here n squared plus 2n plus n. I multiplied both sides with the same expression, and which is a non-zero expression when n is greater than or equal to 1. Therefore, these two are the same. However, if you look at the numerator, we get what? This is just, a minus b, a plus b, sorry, a plus b. So this is just a squared minus b squared. A is this expression, b is this. Square of this is just n squared plus 2n minus b squared, which is n squared. And here in the denominator, I have n squared plus 2n plus n. Okay, so we have this. And here I have what? Now n squares are gone. I have 2n divided by n squared plus 2n plus n. Alright, then what? Well, I can divide both sides by n, and I get 2 here. And if you divide by n, you have 1 here, n divided by n. And here you divide this thing by n, and goes inside square root as n squared. So this will be just 1 plus 2 over n, right? N squared. So I am just dividing both numerator and denominator by n. This is what I get. And then we do what? Here we have several things. 2 over n goes to 0 because 1 over n goes to 0, right? I can write it this way. 2 times 1 over n, and this goes to 2 times 0, which is 0. What about this expression? 1 plus 2 over n goes to 1 plus 0, which is 1. What about this? Here I have a function, square root function, f of x, which is square root of x. And this is a continuous function. And here what you put inside goes to 1, and limit of f of x as x goes to 1, right here, this is, you take this as x, and x goes to 1. Therefore, this limit, sorry, 1 square root of x, this is just 1. Therefore, uh, this gadget 2 over n goes to square root of 1, which is 1, as n goes to infinity. Uh, and then we have what? Well, the numerator is constant. This goes to 1, and this is also constant, so this is just 2 over 2, which is just 1. Okay. Here, uh, okay. Here we use the fact that f of x, which is square root of x, is continuous at x equals 1. Dolayısıyla square root'un içi 1'e gittiği için square root of x de 1'e gidiyor. Tamam mı? Alright. What? Yeah. You mean this like this? Or like this? And squared 2 and no, no, no. No, that's not true. Take square of both sides, right? This is n squared plus 2n. This is just n squared plus 2n plus 2 times n squared times n plus 2. So they are not equal. Okay. Uh, Here is another example. Okay. Limit as n goes to infinity n times tangent inverse 1 over n. Well, n goes to infinity, therefore 1 over n goes to 0. Tangent inverse of 0 is 0. So this goes to infinity and this goes to 0. 0 times infinity, it's not, it's indefinite, right? I mean, we don't know what the limit of something like this. If one of them gets bigger and bigger, and if the other one gets smaller and smaller, the product could do anything. Look at this one, n squared times 1 over n. This goes to infinity, this goes to 0, but the product is n and goes to infinity. Or write it this way, n times 1 over n squared. This goes to infinity, this goes to 0, but the product is 1 over n and it goes to 0. Or it could be like this. This goes to infinity, this goes to 0, and this is the, say, 5. So the result is just 5, right? So if one of them goes to 0 and the other one goes to infinity, the product doesn't have limit in general, right? It's not clear what it will be. You have to work more, okay, to decide whether the sequence is convergent or not. You cannot say anything right away. In this case, this is what we will do. Look at this function, okay, for positive values, okay, and note that tangent x inverse x is graph something like this. Pi over 2 minus pi over 2 tangent inverse x has a graph like this. Okay, y equals tangent inverse of x. But this is not tangent inverse of x. X times tangent inverse of x. It's something different than that. Nevertheless, we can do the following. I can write, so limit as n goes to infinity, n times tangent inverse 1 over n. If it exists, it should be this limit. So actually these are not equal to each other. In general, uh, we have this equality if this limit exists. Okay, if the right hand side exists, right? If this limit exists, then it is equal to this one. At the moment, we don't know whether it exists or not, right? We don't know. Well, we will work hard to see if it exists. I can write this limit as follows. This is just tangent inverse of 1 over x divided by 1 over x. Now it has the form 0 over 0, right? As x goes to infinity, tangent 1 over x goes to 0. 1 over x goes to 0. So I have 0 over 0 case. Well, here we can use a so-called L'Hopital's rule you have learned in 119. So use L'Hopital's rule. What is that? Well, it tells us that we may take the derivative of both sides. Well, let's do that. Derivative of the numerator is this. Derivative of this. Derivative of tangent is 1 plus 1 over x squared. X is just 1 over x here. So square of this times derivative of inside, which is minus 1 over x squared. Right? So the derivative of this, maybe I should write it this way. Let me do it in two steps. So, okay, here we take tangent inverse 1 over x derivative, 1 over x derivative. This is just minus 1 over x squared, and this is 1 over 1 plus 1 over x squared times 1 over x squared. You see, this is cancelled with this one. So what is the remaining term? Limit as x goes to infinity. This is just x squared divided by x squared plus 1, right? 1 over x squared is 1 over x squared. You have 1 here, you add them up and then take x squared upstairs. You get this. And now here x goes to infinity. As x goes to infinity, I can here actually we can do one more step. Divide everything by x squared. So we have this. And now this thing goes to 0. Right? This thing goes to 0. So numerator goes to 1. Denominator goes to 1 plus 0, which is 1. 1 over 1, which is 1. So this limit is 1. Okay? All right. Any questions? Yeah, how did I get this? So you see 1 over 1 plus 1 over x squared. This term here. This is just 1 over x squared plus 1 divided by x squared, and x squared goes up, x squared over x squared plus 1. Okay. Uh, we have a fact stated as a theorem. It tells us the following. If an converges, then an is bounded. Okay. If a sequence is convergent, then it has to be bounded. Of course, this is true. Why is that? If a sequence is convergent to some number, let's say 500, it means that your sequence, uh, almost all the terms of the sequence will be very close to 500. How close? Well, you decide. Let's say 1 unit close. Okay, then we know that by the definition of limit, there is some index. It might be something very big, let's say 1 million. Okay, after that index, so the terms a 1 million, a 1 million plus 1, a 1 million plus 2, they will be all in the interval with center L and radius 1 unit. So they will be between 501 and 499. All of them will be there. And there are only finitely many terms outside, right? 1 million terms or 1 million minus 1 terms. But they cannot go far away because there are only finitely many of them. You just look at the farthest away term, and then all the terms of the sequence will be in this interval plus the ones that finitely many ones, but you can choose something bigger, and that will contain all of them. So that's the proof. But you know uh, to make it more mathematical, let's write down. So we are given that limit of an equals L. Okay. Uh, this means for any epsilon there is some n, right? Since this uh, definition of limit works for every epsilon, I can choose that epsilon anything I want, because this limit is equal to L means that definition of limit given epsilon there is some n works for any epsilon. In particular, it works for epsilon equals 1. Epsilon should be a positive number. I cannot choose it to be 0, but I can choose any positive number I want. So let epsilon to be 1, which is a positive number. Then, by the assumption, there is some n natural number, so that if n is greater than n, then the distance between an and L is less than epsilon, which is 1. So if n is larger than this n, an minus L is less than 1. This means an minus L is less than 1 and greater than minus 1, right? An minus L is less than 1 means this. And this means an is less than L plus 1 and L minus 1. So also the terms whose index less than n big N are outside this interval. So I can choose the following. Let k be the maximum of all these numbers. Maximum of all these numbers. I look at the absolute value of L minus 1, absolute value of L plus 1, and all the absolute values of these numbers, A1, A2, up to AN minus 1, the, the ones which are outside, right? You see, uh, I have the following picture here. I have L, I have 1 unit here, so this is L plus 1, this is L minus 1. So AN is here, AN plus 1 is here. All the AN plus N's are here. And outside, there might be A1, A2, maybe A3 is somewhere here, A5 is somewhere here, and let's say AN minus 1 is here. So what I do, I look at the, uh, uh, you know, all the absolute values of these numbers, AIs up to this number, and also this number and this number. This is a positive number because these are all non-negative and they cannot be all zero, because if this is zero, this means L is 1. But if L is 1, then L plus 1 will be 2. So this is a positive number. It is the maximum of n plus 1 numbers, right? Moreover, moreover, an is less than k for all n from 1 up to infinity. Why is that? Because uh, uh, k is larger than this number, this number, this number, and it is also larger than this one and this one. Therefore, for n larger than n, this uh, this thing is less than this gadget, right? Here you see that if an satisfies this, an is less than what? Maximum of L plus 1 and L minus 1, right? If an is between these two numbers, then its absolute value will be less than the maximum of the absolute values of this. For example, suppose L is minus 5. If L is minus 5, this is minus 6, and this is minus 5. No, minus 4. Absolute value of this will be 6. Absolute value of this will be 4. So the absolute value of this will be less than 6. Okay? So you see, an is less than this k, maximum of all these. Okay. So here we have seen that if a sequence is convergent, then it must be bounded. Say it in a different way. If it is not bounded, then it cannot be convergent. Okay? Uh, the above theorem uh, implies that an unbounded sequence unbounded sequence cannot be convergent. Okay. Uh, for example, right, minus 1 to the power n times n squared is unbounded, is not bounded, and thus it is not convergent. Yeah. Not convergent is exactly not divergent. Yeah. So not convergent means divergent. Okay. Then we ask the following question. Well, if it is convergent, then it is bounded. What about the converse? If it is bounded, would it be convergent? Well, of course, that's not true, right? The alternating sequence 1 minus 1, 1 minus 1, 1 minus 1 is bounded clearly by 1, but it's not convergent. So remark, uh, sorry, uh, a bounded sequence uh, need not to be convergent. Okay. For example, the sequence minus 1 to the power n, which is minus 1, 1, minus 1, 1, minus 1, 1, is bounded by 1, k equals 1, sorry, but it is not convergent. It is not convergent because uh, it's it doesn't get close to any number, right? If it were uh, if it has a limit, let's say L, then what would happen? If you choose, let's say, epsilon 1 over 2, then all the terms of the sequence should be in this 1 over 2 radius, right? So L plus 1 over 2 and L minus 1 over 2. So after some index, the terms of the sequence should be in this interval. But the terms are either 1 or minus 1. It means both minus 1 and 1 should be inside this interval. However, the length between these two, the distance between these two numbers is 2 units, and the distance between these two numbers is 1 unit, right? L minus 1 over 2 and L plus 1 over 2. So this means 2 is less than 1, a contradiction, right? We have an interval of length 1 and it contains both 1 and minus 2. That's not possible. That's why this sequence is not convergent, okay? Nevertheless, we have the following theorem. If a sequence is bounded and monotone, then it has to be convergent because It is bounded means there is an upper bound. It cannot go above this. And suppose it is increasing, then this sequence is increasing like this, but it cannot go above this level. Therefore, it has to accumulate somewhere, here. And wherever it accumulates, that will be the limit. So that's the theorem. If a sequence is both bounded and monotonic, then it is convergent. Okay. We can prove this, but it requires some work. Actually, uh, it's uh, it requires some facts about the construction of real numbers, so-called least upper bound property of real numbers, but it is outside the scope of this course, so I will omit that. That property tells us the following. If you have a subset of real numbers bounded from above, then there is an upper bound so that it is the least upper bound, meaning that anything less than that number is no longer an upper bound. So there is such a real number. That's something uh, uh, obtained from the construction of real numbers. But we will not go into details of that. Okay, just let's see this, but let me try to explain this. Suppose our sequence is bounded from some number k, so my sequence is somewhere here, and my sequence is, let's say, increasing, so an plus 1 is larger than an. So the terms of this sequence, a1 is here, a2, a3, and so on, but they cannot go above k because it's bounded from above by k. Well, what can happen? These numbers should accumulate somewhere, and where they accumulate will be the limit value. Okay, so that's the content of the theorem. Here is an example. Uh, cons Consider the sequence defined by the recursive relation a1 is 1 and an plus 1 is just 6 plus an, and from 1 up to infinity. Okay, so we are asked to prove that or show that uh, limit an exists. So we are asked to show that this sequence is convergent. How can we do this? Well, just let's take a look at the terms of this sequence. Okay, so it is just 1, and then if you put 1 here, square root of 7, and then 6 plus square root of 7, and then 6 plus square root of 7, and goes like this. Clearly, this sequence is increasing, right? Because each time, so square root of 7 is larger than this one. This is larger than this one because square root of 7 is larger than 1. So 6 plus this is larger than 7. So this is larger than this one. Similarly, this is larger than uh, uh, okay, this number is this. Okay, so yeah, so this is larger than this one, but it's not clear, right? Why it is larger? Let's see. Efendim? Okay, okay. So our observation is that this sequence is increasing, and it seems that this sequence is also bounded, right? Because you see, uh, yeah, I guess this is less than always like 6 or something. Okay, let's see. Okay, we claim that an is increasing. Uh, okay, let's see if it is the case. Well, a2 is, so we mean this, of course. An plus 1 is larger than an, right? As n 1, 2, and 3. N equals 1 case implies a2 is larger than a1. Is it true? Yes. A2 is square root of 7. A1 is just 1. And it is true. Now, for general, we will use, for the proof, we will use induction. So, uh, let's use induction. Assume the result for n. So we assume this. An plus 1 is larger than an, and we would like to show, must show for n plus 1. So when I plug n plus 1, I get an plus 2 is larger than an plus 1. Yani n için kabul edip n artı 1 için ispat etmeye çalışıyorum. Right? We assume the result for n and would like to show that it works for n plus 1. How can we do this? Well, let's see. Okay. So an plus 2, by definition, this is 6 plus an plus 1, right? The rule for our sequence is this. Next term is obtained from the previous term by adding 6 to that and then taking square root. But what is an plus 1? An plus 1 is just by induction, it is larger than an. So I have here an, but 6 plus an square root, right? I have this inequality because an plus is larger than this, right? That's my assumption. But what is this? This is just an plus 1, right? The definition of an plus 1. So an plus 2 is larger than an plus 1. So we are done. So the conclusion is that hence an is increasing. So it's a monotonic sequence. We also claim that AN is bounded. Another claim, all ANs are larger than 1 and less than 3. Okay, for all N. Therefore, AN will be bounded. Let's see why this is the case. N equals 1 case, again, let's use induction. N equals 1. When n equals 1, A1 is just 1, and it is certainly less than 1 and greater than or equal to 1. So n equals 1 case is done. For general, so assume an is less than okay 3 and greater than 1. Then for an plus 1, we have what? We have an plus 1. Well, that is okay. Let me write it this way. An plus, sorry, oops. An plus 1 is is equal to what? 6 plus an, right? Well, 6 plus an, but this an is less than 3. So this is less than 6 plus 3, which is 9, which is 3. So an plus 1 is less than 3, and this is clearly greater than an is larger than 1, so this is greater than 7, and that is larger than or equal to 1, right? So we have seen that an plus 1 is again larger than 1 and less than, sorry, less than 3. So an is a monotonic bounded sequence, hence it is convergent. What is the limit of an? It is convergent. I can find the limit. Let's compute the limit tomorrow, okay? Okay, let me stop here.